Hello everyone. Uh, let's today talk a little bit about multiple degree of freedom systems, which represent probably an important step towards working with general vibrating systems, either discrete or continuous structures. In this lecture, we'll be focusing more on discrete systems, mass spring systems, and maybe mass spring damper systems. Let's just get started and see how to proceed with that. The first multiple degree of freedom system we'll need to handle is two degree of freedom system, which is just the first step towards multiple systems, multiple degree of freedom systems. In a two degree of freedom system, what you have is a dynamic system that can be described by at least two independent variables. These variables are changing in time according to initial conditions and excitation terms. Maybe we can use the most simple system, which is a mass spring system like this one, moving linearly, or maybe it can be a mass moving in a plane. So the coordinates of the mass will be x1 and x2, or x and y, or maybe a pendulum or a mass spring system again, but that is spinning while it is moving in a linear direction as well. Of course, we can go and imagine as much as we can different systems that can be described by two independent variables, but let's just focus for now on this simple system of two masses joined by springs and are moving in the x1 and x2. So the states of the system are x1 and x2, masses m1 and m2. We have stiffnesses k1 and k2. Now when we try to write the equations of motion, we'll find that the forces acting on the first mass are the force created by the spring K1, which is always against the motion, and the force acting by the spring K2, which actually is the difference between how much each of the two masses is moving. So if M1 and M2 are moving the same distance in the same direction, the difference between K1 and between X1 and X2 will be zero, so there will be no force acting from this from this spring. On the other hand, if we focus on M2, then the only force acting on M2 is the force acting by the spring K2, which is again opposing the motion, but to be more specific, it will be opposing the relative motions. That's why we can see here x2 minus x1. Writing down the equations of motion, we will find that mass times acceleration will be the sum of forces in the two masses, but in this case, after rearranging, we'll find that the equation of the mass m1 includes also the displacement x2, while the equation for the mass m2 includes the displacement x1. So the system here is called a coupled system. The motion in one state, or the motion of one of the masses, affects the motion of the other mass as well. So they are coupled. This is the definition of coupling, that each the degree of freedom, when some changes happens to a degree of freedom, it affects the other degree of freedom as well. These two equations of motion now have each is a second order, so we need four initial conditions, two for each of the masses. The coupling will enforce this, and the initial displacements and initial velocities of each mass will affect its motion as well as the motion of the other mass. Now let's try to put this in a matrix form. You'll find that we can write down M the capital M mass matrix M1, M2, which will be multiplied by X1 double dot and X2 double dot, Mx double dot, and the stiffness matrix K will look like this, multiplied by X1 and X2, and we get the boundary conditions, the initial conditions as two vectors as seen here. Now the states of the equation of motion here that describes the dynamics of both masses looks so much like the single degree of freedom system equation, but this is a vector equation in which X is a vector, it's a two-state vector, and M and K are 2 by 2 matrices. Recalling for a single degree of freedom system, the equation of motion looked mx double dot plus kx equals 0, which had the proposed solution a e to the lambda t. Substituting back into the differential equation, we got the characteristic equation, which is a second order equation in lambda. Solving for that, we get that lambda is equal to plus or minus j square root of k over m, where j is square root of minus 1. Now k and m are, in our case, in a multiple degree of freedom system, k and m are matrices. So we'll kind of handle them in a little bit different way. We'll start by proposing the solution a e to the power j omega t. In this case, now a is a vector, which we will call later the mode shape. Okay, so x of t, which is a vector, is equal to the vector a multiplied by e to the power j omega t, and here this is the general harmonic motion. Remember that e to the power j omega t is actually cosine omega t plus j sine omega t. Substituting into the differential equation, we will get minus omega squared. Remember, differentiating this twice will give us j squared omega squared. J squared will give us a minus 1, and omega squared is here, and the other one we don't have any differentiation. You end up with a e to the j omega t as a common factor, so you can write down the equation in this form. For a free vibration problem where no forces are applied, if you get a equal to 0, then there is no motion at all, which will definitely not be a good will not be good news for people who work in this field. And e to the j omega t is a general function, so we can divide by it. You end up with this matrix has to be ininvertible. If this matrix, which is k minus omega squared m, again this is given any omega, this is a 2 by 2 matrix. If you're able to invert this and multiply it by the 0, you'll get a 0 equals 0, which is the trivial solution. So to have a solution, we will have to create the condition where this matrix cannot be inverted. Only in this case something will happen. So for this matrix not to be invertible, it has to be a singular matrix, so the determinant of this matrix has to be equal to 0. In linear algebra jargon, we call this the eigenvalue problem, or the eigen problem, in which you will get the eigenvalues omega squared, and these are the values that will make this matrix k minus omega squared m uninvertible. So if we want to find what are the values of omega that will create that condition, set the determinant of the matrix k minus omega squared m equal to 0. The determinant will create a second order polynomial in omega squared. Notice here that omega to the 4, omega squared, and omega to the 0 are the terms that are appearing. So we actually are going to handle this characteristic equation as a second order equation or quadratic equation in omega squared. The solutions you get are going to be in omega squared. The point here now is you're going to get two different values for omega squared, each of which you'll get the square root of. So you end up with two distinct values of omega squared. These are called the natural frequencies of the system. I didn't go through the algebra. It's not really difficult, but it will make the problem look a little bit ugly. What I wanted to focus on here is that these values of omega are not related at all to square root of k over m for any of the masses or the springs. They are a combination of stiffnesses and masses affecting each other. Remember, this system is a coupled system, so the motion of one degree of freedom or one of the masses affects the motion of the other mass. Thus, we are going to get two natural frequencies. If we extend this logic for 3 degree of freedom system, you'll get 3 natural frequencies. For 4 degrees of freedom system, you'll get 4 natural frequencies, and so on. Let's now demonstrate this idea using numbers. So the masses will give M1 9 kilograms, M2 1 kilogram, K1 24 Newton per meter, and K2 3 Newton per meter. In matrix form, this will give us this matrix equation, 9001 and 27 minus 3 minus 3 and 3. To get the natural frequencies, we will propose again, here's the harmonic solution, use that and get the determinant. You'll find that you'll get two distinct values for the natural frequencies, omega squared equal 2 and omega squared equal 4, or omega 1 equals plus or minus root 2 and omega 2 equals plus or minus 2. These two eigenvalues will give two different what we call eigenvectors. I'll skip now talking about eigenvectors and mode shapes for a while and come back to them later.